Morning, everyone. Our team for going to be talking about digital image processing today. I'm Dave.
I'm Mark.
I'm Jeremy.
I'm Brian Blanky.
I'll start with the background. Pretty much digital image processing, you just have the image input from either camera or video, and you digitize it from picture, video, and then the point is you then process using complex algorithm using software like MATLAB or Adobe Photoshop, etc. And so the point is that you want to enhance the image quality and bring out the details that's of interest, such as edge detection or removal of noise, smoothing out the image. There's all very wide applications for digital image processing, such as the medical, or law enforcement, industrial inspections. The first image you see is of the MRI scan of a heart. You can see the edge detection lining after you apply the complex algorithm. And on the right, you can see the inspection or the picture so that they're just making sure the product is what they want. We'll look at one technique called segmentation. Pretty much, it's just you group, subdivide image into its component regions or objects. It's not perfect, but it's just so the computer knows or recognizes objects. For example, here, that's the input image in the first on the left, and then on the right, after segmentation, it just recognizes it as a circle. So there are two main common types of segmentation. First is thresholding, but for our project, we're interested in edge detection, so we'll look at the second technique. Why we are interested in edge detection is pretty much to trace the outline so that it can detect by our camera. These are the edge models, three main ones, from left to right: step edge, ramp edge, and roof edge. Pretty much detection will be based on the grayscale from going from 0 to 256, I believe. And then further breaks down into 4 steps. You first start with smoothing. You remove any noise that can happen from when you convert from analog with the original image, and then you load it up the computer. And then you want to enhance the image, where you want to add some contrast, brighten up some images, areas that's not clear, so sharpening. And then the third detection, you want to actually trace the outlines of whatever you're looking at. And then finally, you want to actually identify the exact location where you want to manipulate to your liking. And then finally, we'll just look at the brief, detection of operators. There's many, but these two are very basic. They're called pre-wet and Sobel. The zeros you see are the horizontal vertical. That's how it compares, I guess, as it goes through the filter. The only difference from the pre-wet and Sobel is that the coefficients, the -0.02, that's how it detects the center. But the only problem is that when it's exposed to a high level of noise, both of these operators fail. So then we will have to go to the Laplacian operator, but that's beyond the scope of this presentation, so I won't go into the details. So pretty much what this all means, we'll just take a look at the example picture. Here's the original image, and when you apply through the filters, it traces the edges. They're very similar, but the right side is a Sobel. It's a little bit better. It's finer details because it has a smoothing features.
So along the lines of what else your digital image processing can do is I'm going to talk about anisotropic diffusion, which is used to remove noise from images. And you might not think that images actually have noise, but because they're just a reconstructed signal, it's entirely possible. Noise can come from anywhere, from power lines to light, and it makes it look like it's not supposed to. So if you take a look at these two images, one is diffused and one isn't. And here we have a little bit of light, and it makes the features of the flower harder to see. And there's a diffused one on the left side, and you can see the features a little bit better, and it's a little more clear image, and it takes some of that light noise away. And along the line, or more of what digital image processing can do, there's pixelation and anti-aliasing. Now what can happen is when you zoom in on a piece of an image, it starts to look like not the image. So if we take a look at this cat here, when you look at the forehead of the cat, really zoomed in, it doesn't look like the forehead of the cat anymore, which is sad. We don't want that to happen. So to solve this problem, we use anti-aliasing. If you took 366, aliasing is an effect that will cause signals to not be able to be reconstructed. So it's hard to find the original signal once that happens. So if you use that definition, then anti-aliasing would be the minimization of distortion and a small-scale reconstruction of a piece of an image. So this is an aliased signal. It got, I think it had too much light exposure, and it started to look a little bit goofy. Houses don't usually look like that. So a very common type of anti-aliasing, if you've ever played video games or anything, you know, running around in Skyrim and you zoom in on a piece of grass, it doesn't really look like that. So what can happen, instead of jagged sharp edges like that, where there's really a 1 and a 0 on a grayscale image, so you can go from full black to full white, what it can do, it can shade those images together, and it gives it a nice smooth blend and doesn't look as jagged anymore, and our jagged sharp edges on this picture look more like a line, like it's supposed to. And the reverse of that, we can actually use pixelization. So if people want to remain anonymous, or there's, you know, nudity on TV, which nobody wants to see, that stuff's gross, we can reverse the interpolation and enlarge them and create a more jagged image. This person wanted to remain anonymous, so we went ahead and pixelized that image for them.
Computer vision uses vision systems and image processing in more industrial settings to make decisions on a specific process. And it's becoming more common in manufacturing facilities because it increases the speed of production, and it also increases the speed of inspection of products, and eliminates the need for an operator to be present at a line in order to inspect product. Just to run through the methods of a vision system. The first stage of the vision system is the image acquisition, and this is most commonly done with some kind of light sensitive camera, but other techniques can be used like ultrasonic cameras and also radar. The second stage is image pre-processing, and this is a stage where more basic general image processing is done. Things like the anisotropic filters that we saw earlier. And they kind of just reduce the noise of the image and also can reduce blur in image due to things like vibration in machinery. And the third stage is called feature extraction, and this kind of intakes all the features of an image regardless of really what you're actually looking for. Like it'll take in any edge of an image if you're doing edge detection. It's getting kind of hard to see, but the fourth stage is detection and segmentation. And this kind of separates out what you're actually looking for in an image. So if you take an edge detection of an image and you're not actually interested in all the background edges, and you're more interested in, let's say, the edges of a box, then you can use segmentation to only look for like hard 90-degree corners of the box. And now you can't really see down below here because there's a picture in the way, unfortunately. But the next stage is a higher level processing that can be used to, it's more of a specific application for the specific situation of what you're looking for. So it could take these corners of the box that you're looking at and find the distance between them to determine if it's a large box or a small box. And then the last stage would be the actual decision making in this process, which would be determined by if the box is large or small. Maybe a paddle would push large boxes into a bin on the right and small boxes into a bin on the left. Another application of image image processing would be object identification. And this can be used on a production line to quickly, without the need of an operator, to differentiate between classes of objects and also do things like count objects and just see if an object is present in your field of vision. Say you have a bag of parts that need to be shipped out with some kind of cabinet to be assembled. You need to be able to easily and quickly count if you have the right number of screws, if you have the little Allen wrench that comes with it, and other little things like that. Fault detection is a little bit more complex, but is becoming more prevalent in industrial settings, and it kind of uses multiple image processing techniques that we saw earlier to just make sure that a product is kind of up to requirement. So you can see in this picture, these 4 spray bottles are being inspected for several things, including the level of the liquid in each bottle and also the orientation of the cap on top of the bottle. And this can be used to quickly inspect to see that all the requirements are being met. Can go much faster than an operator picking up each individual bottle to see if it is okay. Moving out of industrial settings, object tracking is another common use of application of image processing. And it really has a predetermined set of images that it looks for, and it takes several points and looks throughout the entire image for it, like 2 headlights and a grille on the front of a car. And this can be used to determine the position of an object in your field of view. Optical flow is similar to object tracking, but doesn't actually track a specific object and kind of just detects motion in separate pixels in your image. So, like in these 2 pictures, it kind of, the motion that is displayed by these 2 animals is shown in vectors, so you can see as this pixel moves from here to here, you can kind of gauge its velocity and also its acceleration. The last is ego motion, and this uses a set of stationary objects and a camera moving around it, and it uses the perspective of the objects to kind of gauge the position of the camera system. And this is being used to map like underground or underwater settings that are really hard to map using a GPS system. And also using these images and your position, you can create a 3-dimensional space in a computer software program. You can kind of map out like a cave or the ocean floor or something like that.
So we've talked a lot about the techniques that go into image processing technology. Some of the tasks that image processing technology is good to satisfy the requirements for are the points listed here. Digital image processing is the most practical technology for the statistical classification of images, for feature extraction, graphical projection, and pattern recognition. So I'd like to talk more in depth about these tasks. Statistical classification is identifying which sets of subcategories new observations belong to. And this is based on sets of data whose category membership is already known. So you group these categories into explanatory variables, and those are individual observations which are analyzed into quantifiable properties and categorized based on either categories or types, integers, or decimal values. An example of digital of statistical classification is in digital camera color filtering. And how a digital camera works is it imprints the intensity of light on a phosphate cell and reads the intensity of the light at each pixel. The way that color is achieved in a digital camera is by it takes the intensity of light of a red, a green, and a blue layer of the image and combines that into the full spectrum of colors. So to do this, statistical classification is used, and it does that by placing a Bayern filter over the phosphate layer. And this is a pattern as shown in the image here. and the full color spectrum of the image is constructed by using information of the colors from all the nearby cells, which estimates the colors of each pixel. So by observing the data of the nearby cells in the Byron filter, it's able to combine all the spectrums of light to make a full color, and that's how the colors are estimated in your digital camera images, and that is called interpolation. Feature extraction is another task of digital image processing. It involves simplifying large quantities of data to describe, so if you have a large set of data and you need to describe it accurately. It reduces processing, also because when feature extraction is necessary, it's suspected that there is a large amount of redundancy in the data. So you could have similar measurements that are repeated in different formats, like you could have meters and centimeters. So to reduce redundancy, you would extract the data into one measurement. So it's expected that the features of the set will extract all the relevant information to perform the desired task. So in image processing, feature extraction is important in edge detection, where edge detection works by determining where the brightness changes sharply. So that's one way feature detection distinguishes where edges are. Another use of feature extraction is in curvature edge detection, which cross-correlates the image between time lag, so it can tell like where things have moved. And in motion detection, changes of position relative to the surroundings detect how the image is moving. Another use of feature extraction is in thresholding, where it forms grayscales of the image and extracts the features needed to reconstruct the image. The hue transform is where if you have an image of objects that are pretty common, such as text, written text, which is imperfect, the hue transform uses mathematical functions to estimate, based on a voting procedure, what the shape of the object is likely to be. So if you are taking an image of text and it thinks it looks like the letter T, it can guess based on the structure of the lines that it's a T, and that's how it helps reconstruct the image. Graphical projection is another technique of image processing. The process of projecting a three-dimensional object onto a planar surface with mathematical computation. This is kind of similar to how an architect would draw 3D objects to make them look 3D on a 2D sheet of paper. In digital signal processing, this is accomplished through mathematical functions, converts 3D objects into a 2D image. Computations involve Fourier transforms and Hermite functions. So as you can see in this image of Egypt, the original image is split up into its baselines, and using functions, the baselines help determine how to construct the image on a 2D sheet to maintain its 3D appearance. Pattern recognition is another task of digital signal image processing, which features distinguish objects from others. Algorithms classify objects or clusters of an image. So some applications of pattern recognition is face recognition, fingerprint identification, and document image analysis. It helps with 3D object recognition, and it helps robots navigate. So this is a way where image processing software can detect objects and patterns to help reconstruct them in the image to match for security purposes. So that's the end of our presentation. Does anyone have any questions about digital image processing?
Ryan, when you talk about the colors, why didn't they just use the primary colors? Why is it RGB? Why is it green?
For the baselines?
Yeah.
Well, are you talking about the Byron filter?
Like interpolation slide, whatever.
Yeah, so, to reconstruct the image the way we see it, the primary colors that we see are red, green, and blue, and constructing those creates the full color spectrum. And if you look at the Bayern filter, there's more green cells than red and blue, and that's because our eyes are more sensitive to green light, so that's how the Bayern filter reconstructs the light to estimate what the color is at each pixel.
More questions? Yeah, how are you going to implement the edge detection?
So, the techniques we described here for edge detection are part of the hardware and the software that we're using. So we just have mostly a software
So it's going to be
implementation.
more in software.
Yeah.
So what's the mathematical operation for edge detection?
Well, the edge detection operations would be handled through the code. So implementing the math, we might need to tweak it, but those functions would likely be in the code already based on examples of previous work that we would be.
So the software is going to be given to you by the company?
Well, we're using OpenCV.
Yeah, well, I mean, I could draw this if you wanted to see it, but what'll happen is, so if we do have like a steel strip right here, right, and we just have some image with some noisy gray stuff, we're gonna have a higher density of edge detection pixels right here, right?
Yeah.
So we can split the image up. We're not gonna use the entire image because that would take a whole lot of processing speed, so we can just split it into little, 2x2 matrices, and depending on where the density is, we can take this mid-pixel point and just add them, like do the fission or whatever you do to calculate the center line. I can't think of the algebra inside my head right now. But if you use these 2 points, you can calculate a center line right there, and it would just be based on the density of where the edges are.
So it's just going to be, if you represent the data in a row as x of n, what you essentially do is x of n minus x of n minus 1 to get the edge location.
I didn't follow that, but maybe. I'm sorry.
Edge detection is an extremely simple operation, right?
Well, yeah, based on where the edge 1 is and the edge 2 is
How do you get
minus
the
that.
location where edge 1 is locating the edge?
How do you?
Are you going to using MATLAB toolbox or?
What I think you're asking is, you know where the edge is in the image, but how do you quantify the position of the
Yeah.
edge?
Right.
So we can detect which pixels are triggering where the sharp contrast between colors is, where the edge will be. So using that, the software can output data on where the position of the edge is in the image, and then we can just take the second edge minus the first edge and divide by 2.
Like we wouldn't be able to tell you how many feet this is because we don't know where the position is going to be relative to the actual steel strip. So they could put it anywhere. I mean, it's going to take some, what do you call it? I can't think of the word right now. But because it could be like, 2 centimeters away or 3 feet away, we wouldn't be. We know where the pixels are, but it wouldn't be able to tell you the relative distance in feet or meters or whatever they want.
And you are tracking the center point from frame to frame?
Yes.
So yeah, they would be getting a set of data of where the edge is at time intervals.
Any other questions? Thank you.